Hello everyone. Today we are going to talk about acid-base reactions. This is 4.8 Introduction to Acid-Base Reactions from Unit at Glance. Okay, so think about some things you use in everyday life, which is acids and bases, and write it down. Did you know that pH is very important for gardening? So one of the examples are these flowers, which have different colors when grown in different um, pH, soil pH. So if it is acidic soil, you'll get blue flowers. If it is alkaline or basic soil, it will be pink flowers. So today we are going to talk about properties of acids and bases and talk about a couple of theories. One is Arrhenius acids and bases and Bronsted and Lowry's acids and bases. And we will touch slightly on Lewis acids and bases. So properties of acids and bases. So acid bases are sour to taste, and if you have listed some things, I think you might have listed orange juice and things like that, which are acidic. These are electrolytes. That means they conduct electric current when they are dissolved in water. They also react with metals to give a hydrogen gas. The pH is below 7. So anything below 7 to 0 is acidic. And what's a pH? pH is the negative log of H plus concentration in the solution. So we use a couple of things to test the pH. One is a litmus paper, which turns red if you dip in acid. Phenolphthalein is one of the indicators. There are a lot of indicators. Phenolphthalein is one which changes color. If it is acid, it's clear. We also use pH meters to check the acidity or concentration of H plus ions. So here are some examples of strong acids. Now strong acids dissociate completely. That means they ionize in water. So for example, HCl becomes H plus and Cl minus. Whereas weak acids dissociate partially. That means only a few ions will dissociate in the solution. So you need to memorize these strong acids listed here. So that you know when you're doing a net ionic equations, these are the strong acids which will dissociate completely. Okay, examples of acids. Check if you have some of these in your notes. Properties of bases. Bases are slippery to touch. So used in soaps, are electrolytes as well because they dissociate. They are bitter to taste, so some of the medications have bases which are bitter to taste. pH is above 7 and the maximum is 14. So the higher the pH, the more basic it is. The lower the pH, more acidic it is. The litmus paper in a base turns blue and phenolphthalein turns pink in color if you add phenolphthalein to that solution. Now if you do pH meter, it will give you the pH in a digital form. These are examples of some bases, weak and strong bases. So similar to acids, strong bases dissociate completely. Weak bases do not dissociate completely, only a few molecules will dissociate. So you need to know these strong bases. Acids. And here are some examples of acids strong bases. So Arrhenius. So what are acids and bases? So Arrhenius came up with a theory for acids and bases. So he said any substance when dissolved in water increases the H plus or hydronium ion concentration. So H plus and hydronium are same thing. When H plus combines with water, it forms a hydronium ion. So you can write either hydronium ion or H plus. They mean the same thing. So that means an acid donates a H plus ion. whereas a base, any substance which increases the OH ion concentration. So it donates a OH ion. So let's look at some examples. So look at these. The first one is HCl. So it will donate the H plus. So it will split into H plus and Cl minus. So it increases the concentration of H plus when you put it in water. So that's why it's an acid. Whereas look at NaOH. It has a OH, so when it dissolves in water, it goes Na plus and OH minus, so increases the OH concentration. So that's a base. So see if you can figure out the other acids and bases. What about these? Can you identify which one is an acid, which one is a base? Think about it. I bet you can't, because if you said NH3 was an acid, NH3 is actually a base. And so is sodium carbonate, which is in your baking soda or baking powder. So this was a drawback for Arrhenius model. If it doesn't have a H plus dissociating or a OH minus dissociating, then we can't identify which one is acid and base. So we use Arrhenius model a lot, where we have H plus and OH minus in the compound, and which split up when they are dissolved in water. But when there is no H plus and OH minus dissolving in water, we look at a new model, which is Bronsted and Lowry. So Bronsted and Lowry's model said that acids are any substance that donate proton. Bases are any substance that accepts a proton. So think about what's the difference between Arrhenius and Bronsted and Lowry's model, right? Okay, so let's look at how we identify Bronsted and Lowry's acids and bases. Think about these questions. Okay, so here is an example of Bronsted and Lowry's acids. Okay, so you have to look at a reaction to figure out if it is a Bronsted, Lowry's acid or a base. So if you look at the equation here, HCl plus H2O giving you hydronium ion plus chloride ion. So in this case, if you look at the reactants, the hydrogen is transferred from HCl to H2O. That means HCl donates a hydrogen. So that's why it's an acid, whereas H2O accepts a hydrogen. So that's why it's a base, right? So whatever is the acid, what is left, it's Cl minus, right? So it's called as a conjugate base. So it was an acid here, it donated the H plus. Now the remaining part of that acid, which is Cl minus, is a conjugate base, and hydronium ion is a conjugate acid. So why is that? So if this reaction was to go backwards, then it's H3O plus will donate hydrogen to chlorine. So that would be H3O plus would become an acid, and Cl minus is become a base. Here's another example. NH3, which was one of the exceptions in Arrhenius theory, right? A problem there. So NH3 when added to water becomes NH4 plus and OH minus. So observe here, which one is donating a hydrogen? Here water is donating a hydrogen atom to NH3. So water is an acid, whereas NH3 is a base. Now think about the product side. Which one would be an acid and which one would be a base? So here ammonium becomes a conjugate acid because it is going to donate the proton to become NH3. H plus is called as proton. So this is a conjugate acid, and OH is a conjugate base because it will accept a proton to become H2O. Okay, if you have any questions about this, make sure you write it down. Okay, so here is the example which I just showed. So a conjugate acid is a particle formed when a base has accepted a hydrogen atom. So hydrogen ion. So NH3 accepts a H plus to become conjugate acid, whereas H2O donates a H plus and becomes a conjugate base. Conjugate acid base pairs. So in this case, if you look at, water is always dissociating into H3O plus and OH minus. So here H2O and OH, that's H2O and OH, they are acid base pair, whereas this H2O and this H3O plus is an acid base pair. Amphoteric. So you have seen in the two examples, water acts as an acid or a base. So it's called as amphoteric. It can act as an acid and a base. Why is this? Because water can accept a proton, act as a proton donor, or it can also accept a proton. So it can go either way. So it's called as amphoteric. These type of molecules are called as amphoteric. The last one is Lewis theory. We won't go in detail on this one, but just for you to remember, in Lewis theory, the acids are electron pair acceptors, means they accept a pair of lone pair of electrons from another atom, whereas bases are electron pair donors. So they're opposite of how the protons are accepted and donated. So that is acid-base theories. Make sure you answer the 5-question quiz on Canvas. Thank you for watching. Bye.